I'm going to start working on my Hickok OS-10 now. I've had it in my possession for a long time. In fact, it appeared in an earlier video way back when I was working on the ICO or when I was just finishing it up. It's time for me to start looking at the insides of this. So I've got the back cover off. I'll tip it on its side so you can get a look. I've got the OS-10, which is an oscillator, by the way, tipped on its side. But I'm going to turn the camera this way so that we can look at some of the things on in the area where the tubes are located. You can see this is actually just a gauge. It sits on a little drum and it just has the paper glued onto it. But the business part of it is that capacitor that you see down there, the air capacitor. Only 4 tubes in this. There's 2 that do oscillator work. One's a mixer, and then there's a rectifier too. The serial number on mine is 13066, which puts it into the later schematic age, and I'll go over that a little bit later on. I believe that's the power transformer right there. Yeah, that's the power transformer that looks like anyway. Looks like there's a couple of, I don't know if that's an oscillator back there with those 2 capacitors. There's a fairly large box sitting right there. I'm going to have to figure out what that is, but it's situated where some of the controls are. Huh. I don't even know what that is. I'm going to have to figure that out, I guess. I'm going to rotate this around a little bit so that we can look at the underside. And when I looked at this at first, I thought, hey, this is great, man. Look at all the new capacitors that are on here. Not just here, but the 2 that we looked at over by the dB meter. And I thought, man, these are the new type. Somebody's already gone in here and done some work. I may not have to do anything, but as I've been looking at it, you know, I probably would have redone it because it's kind of like just suspended on these, you know, all the components are suspended in midair here. I'll try to neaten that up a little bit. Most of the capacitors that were put in here are not the right spec. One of the things I noticed was that this capacitor right here, I'm not sure what the purpose of that one is, you know, I mean, compared to what's on the drawing. First, one end of it goes to ground down here, but when we come up, or chassis ground anyway, when we come up here, we see that it's attached to a switch. Follow this lead up here, right here. It's attached to a switch right there. And when I look in the drawing, that switch doesn't really exist. You know, what do I want to do about that? I think maybe one of the first things I'm going to do is get rid of that switch and wire this thing in the way it's supposed to be. But yeah, this, from what I can tell, doesn't belong in this version of the oscillator. I've checked the capacitance on these 3 capacitors inside here, and they're out of capacitance anyway. They're out of spec for that. I don't even need to do a leakage test on them, so they'll have to be replaced. And these 2 capacitors here are the wrong spec. They're showing, those are all 22 microfarad. In my drawing, that's an 8 and a 12. I know I've got an 8 on hand. I don't know if I have a 12 or not, but this is just starting out. I think that those 3 there are going to have to be the Y-type capacitors because at least 2 of them are anyway. They have to do with the power. coming in, and they're actually, before it gets to either the transformer or the rectifier, it's coming right in off of the line. So I have to put a couple of those Y type capacitors in there. Um, I really have some questions about all of this stuff. I don't know if it's a combination of, they put together two different drawings and came out with this. I'm not sure how we arrived at where we are right now, but I've definitely got some issues I've got to iron out here. This is a modified version of the revised drawing. In it, I've created unique identifiers for each component so that they can be cross-indexed. The identifiers employ the numbering scheme, same as in the original, but also includes a unique counter separated by a dash. Note that I've also labeled the pin numbers for each tube. Quick circuit overview. At the upper left, we see the mains power coming in through the switch S1 and through two safety caps before getting to the power transformer. Then onto the 1V rectifier and two filter caps. The RF oscillator circuit includes the 6J7 tube, switch S3, a multi-select that connects the active coil while grounding non-selected ones. And there are also two variable caps worth mentioning. The first acts as a frequency tuner within the selected band, and the second performs even finer tuning. All of these controls are connected to the 6J7's control grid. Modulation of the RF signal is handled by a 6C6 configured as a negative resistance oscillator. I wound up having to look that one up and found an application note from RCA dated back to 1935 where they stated that a negative resistance oscillator will occur when the screen grid is more positive than the plate, and when a capacitor and leakage resistor are configured between the screen and the suppressor, which is what we see here. Switch S4 acts as a multi-select switch that allows tuned circuits to be switched into the oscillator. And the AF coil is part of a tank circuit that provides 400 cycles, and another coil shown off to the right there is listed as providing 0 to 10 kilocycles. Below is an external modulation jack that more or less barges in over the others when a signal is provided over it. The output of the modulated signal goes through the mixer and an attenuation pot when the switch S2 is set to AF. The other selections address greater ranges of attenuation, but only for pure RF before going through the pot and to the output jack. Finally, there is a dB meter, along with a resistor and two caps, which apparently function as a standalone device. The meter is not connected to the rest of the OS-10 other than sharing the same chassis. This sub-device measured power logarithmically and would presumably be useful in sound and audio applications, although I'm not entirely sure what its function is here. I started by removing the can housing the three capacitors, including the two power caps. In its place, I installed a couple of terminal strips using existing screw holes in the chassis. Here you can see that I have pre-wired the grounding for the terminal strips, but also note that I pre-wired the interconnects for each capacitor I plan to mount here. Here I've removed the cap C3 from the earlier drawing. I've also removed the mods, including the bulb, the switch, and its associated capacitor. I've replaced one of the electrolytic capacitors and the non-power cap from the can, moving it closer to where it is used. I've also installed missing cap C11 and moved C6 to connect through it. Finally, I replaced the remaining orange drops both here and on top near the dB meter. I mounted a terminal strip to support two of the caps and move the third closer to where it is used. We're now waiting for delivery of the orders to finish bringing this OS-10 back to its intended design. I finished replacing all the capacitors. Well, not all of them. I still have one more to replace right here. It's just not the right size, but it's close enough. Show you what I've done here. Back in the corner I mentioned this is C11. It wasn't installed at all, so I inserted it into the circuit where it was supposed to go. On the left hand side you can see these are the two filter capacitors. One is 8 microfarad and the other one is 16. Now that 16 is supposed to be 12, and I was going to order a new one, but I found out that they don't make the 12s. So it's a filter capacitor. 16 should be close enough. I also had a 10. I probably could have put a 10 in there instead. These two are the replacements for the mains capacitors, the main filters. Those are Y2 type capacitors. When they fail, they should fail open. I brought in a new power cord. The red line that you see there is that there was no fuse installed in this thing, and in fact there isn't even one in the design, but I did decide to go ahead and add a fuse here. So I just drilled a hole in the chassis and mounted it there. What else have I got to do? Yeah, as I said, I have one more that I have to do. I had planned on getting some kind of a jeweled lamp or something here. That hasn't come yet, so I still have that to do. But by and large, it's put back together as it's shown in the drawing. And I've got a frequency counter sitting next to it. It's an old one, but it's not that bad. I think what I'll do is plug that in. I don't have an audio jack, so I've taken a little piece of cardboard and insulated that little prong so that it doesn't touch ground. And I'll just go ahead and strap in a couple of leads here. I'll go ahead and put some power on this thing, see what happens. Keep an eye on. We got glow on one of the tubes anyway. I don't know if that's a reflection of one of the tubes or whether that's actually glow. Yeah, very faint glow on that one. And I think I see a glow inside there. Okay. So the fuse is holding, the power is holding. Let me turn this around. I've strapped in the leads from this frequency counter, and I'll go ahead and turn this thing on. Well, actually I should be reading something right now, but I'm not. Let me see what I've got here in the way of knobs to play around with. That reads something. So when I switched from RFX1 to RFX10, I started to read something here, and on this, that's 150 kilohertz is what it's, because it's switched up to megahertz. This thing goes well, let me see what happens if I put it on auto. There we go, 150 kilohertz. And we're on the bottom one, and that's 150 kilohertz there, I guess. A. So the way that it reads, I guess, is A from the bottom, A, B in the first major one, C, D, and then E, F. And I don't know what's way up on the top there. Oh, it goes all the way up to G. Okay, so the one on top must be G. So 150, it's reading about right. Let me switch over to B. Well, that doesn't look right. 23 kilohertz. It should be something like 400 according to that gauge. Let me, what does this knob do? Okay, all right. So that's a power, that increases the power of the output, and we're reading around 400 right now. So that looks good. Let me see if I can turn this down now. Okay, so this is a coarse adjustment. This is a little bit finer adjustment in terms of power, not the frequency. Let me go to the next band. That says 1 megahertz. And that's about right, 1 megahertz. Let's try the next band. Oh no, the next band is over here. And that dropped off to 0. Let me try increasing this power. It doesn't pick it up. So I have to do another coarse adjustment. 2500. Okay, so I made a coarse adjustment to RF times 100, and I've turned the gauge, the fine one back down to the middle. 2500. That's the fourth band up. Yeah, that's about 25. It's between 24 and 26, so that looks pretty good. So we're up to D. See what happens if I go to E. That zeroes it out. Now I don't have any more. Let me see if I can bring this one in by just going super high. I've got this one turned up all the way now, and that's up to RF times 100. And we're at 59, 40, 60, 6 megahertz. Yeah, so it's, if you look at it, it's just below 6 megahertz on there. So I probably run out of space. I don't know what's going to happen when I go to this next one. Yeah, that dropped off. I'll try the AF. AF doesn't do anything. Well, let me try it taking this fine one all the way down to the bottom. See if I get anything back. Okay, so it's band F, and I've got it at the lowest setting, which is, I guess that's 8, getting close to 7.5 or 8 megahertz. Let me go down to E and turn it up the other way and see where I lose it. What I'm going to do now is go to the other end of the scale, but on this E band, and turn it all the way up. There's 7. There's 8. Okay, starts dropping off and acting wacky at just above 8. And that's about what we're getting on the other side. So, okay, we kind of know what we have there. What does the AF do? It drops right off. So let me lower this all the way down. It says 555.9. I thought it was 600. Oh, that's right. I adjusted this. 555.9. That's pretty close. Okay, this thing's actually, for the ones that work, are, the frequencies read out pretty good. Let me think about what we've done so far. Shut them both off. I think what it tells us is that, we're having some loss the higher we go in the frequency range. And one thing I can say for sure is that this thing goes up into the megahertz, 8 megahertz. I didn't see the ability to drop it down below, what was it, 100 megahertz on this thing? Let's turn this all the way down and see where the bottom is. Looks like 90. Let's try that. That says 240. Oh, let me turn this thing up to, still says 240. Oh, I've got it on B. Yeah, that's about right, 240. Okay, let me put it on A. Yeah, 90 may be the lowest that this thing goes. That should be below 90, okay. 90 kilohertz is the lowest this thing goes, which when you look at this, this oscilloscope that I just got done working on, this Hickok, the highest band it's got is 30K. So, but it'll read higher than that. It's just that that's what they set the ranges at on there. I don't know why. But I may plug this into this Hickok that I just got done rebuilding and see if I see what the wavelengths look like. I have the ICO lined up alongside the Hickok oscillator right now, and I've got it set to that same band. I think that's band A, and the frequency looks like I've got it somewhere around, mid 180, 190, somewhere in there. Kilohertz, by the way, kilocycles. We've got that same kind of wave showing up on here, and I can say that it's a little harder to bring the signal in on this than it is on, say, the WaveTech, which is a brand new device, obviously. And this one I haven't finished restoring. I'm getting to the point now where I'm just trying to figure out what's wrong with it. Just identify problems right now. So when I get to a point where I'm not sure what to do, I usually like to just start taking measurements of stuff and see if I can get anywhere that way. Right now, I'm not sure what even most of the components are or where they're located. If I look at this, let me turn this around. They've got several components that are underneath these two boards here. And there's quite a few of them, actually. I mean, a whole bunch, and you can't get to them because they are nailed in place. So, got to be careful. I think I turned the power off on that thing, but that's not going to help me anywhere around in there, that's for sure. But anyway, yeah, I need to know for certain what's underneath those two boards, and then I need to start taking measurements on everything. And usually I start with resistors and see where that takes me. I may also, that silver box that I talked about earlier, that's almost certainly where the oscillators are for A through G bands, um, are tucked away inside there. I wouldn't mind taking a look in there and seeing what that looks like. Here's the inside of that box. I was able to get it off, but I had to use a torch to do it. My soldering iron failed me again. It's not hot enough to take anything off like that. There's some very fine work inside here, fine wire with those coils. Looks like all the coils are connected nicely. 1, 2, 3, 4, 5. I'm counting 6 coils. One of them's big gauge wire. The rest of them are all pretty small. Obviously the box is to keep it clean and to keep your hands away from this work. I thought that perhaps I might be able to pull the switch out, but that's with conventional types that I've run across where the oscillators are connected. You know, they're part of the switch basically. That might be some corrosion inside there. I don't know if that's dirt or what. I'll give it a shot, try to clean it up a little bit, see what we come up with. Avoiding the fine wires as much as possible, I cleaned up the switch housing and the switch contacts, then soldered the cover back in place. I then cleaned up the variable capacitor and its surroundings before putting the tubes back in their place. I did manage to keep the two micas. Those are still in good shape. I replaced the 3 resistors that were up on top of that switch there. Those measured out of spec. Down here, I think I showed those capacitors in an earlier clip, but I've also replaced a bunch of resistors down here, about 6 of them, I think. And they were actually behind the board. It was enough trouble to get them out from behind that board. I just decided to put the replacements on top of the board. It doesn't look too bad that way. And finally, I put in a jewel lamp in there. It's not original. It's not how these things were originally, but that's what I did. As far as jewel lamps, I learned a lesson. This is the first time I ever really bought one, but the guy who sold it to me kind of taught me a lesson that even though these are pitched as good quality metal ones, they're not very good actually. And it was the guy who I bought them from that told me about that they're not that great. And that's what I have installed in here. And in order to get it to work, I've had to jam a little piece of cardboard in there in order for it to light up, you know. So he was absolutely right about that. And what he sent me was, I ordered 4 of them, and he sent me 2 of the bad ones, and then he sent me 2 of these fenders. And these are, you can tell, are much better quality. They look almost the same, but they're a lot more sturdy. The metal is just a little bit thicker. It seems like it's more solid. So If this goes bad and stops working again, I'll go ahead and replace it with one of those fenders, but I'm going to leave this type in for right now because that's what I put in. Uh, that's about really all that I've done on the inside. After changing out the capacitors and the resistors, I want to just go through and check the bands again just to see how far I got. The last time I think we got to like 8,800 kilocycles, which is 8.8 meg when it started dropping off. So we'll just switch through the bands and see what happens. This is A, by the way, and that's set at 150 and we're reading 151. Band B is showing 403, which is pretty close to what it is. Band C is showing 1 megahertz, and we're a little bit over 1 megahertz on that dial, and that's a little bit over here as well, but not as much. Band D is 2.5 megahertz, and that's about what it is for D on there. And band E should be right about 6, and we are just a little bit less than 6 on there. Now there's a bug on this fluke here. It's getting old and outdated, and basically the auto range on there doesn't work anymore. So I have to leave it on the range that it's at, which means that it's going to register an overflow when I go to the next band, which is band F, and it should be 14.6, somewhere in that area. But with the overflow, we're going to wind up losing the most significant digit. So instead of showing 14.6, we're seeing 4.6. So we have to keep in mind that it's dropping one of them. Let me show that it is actually going. I need to turn this knob. If I go to the low end of this band, I can get it into the high 9s. There, we're just under 10 megahertz. And you can see that we no longer have the overflow, and we're at 9 plus right now. So basically we are reading stuff at higher frequencies than we were before we replaced, did the recap and changed out all of the out of spec resistors. Let's go all the way to the other end of that scale. What happens when you get to the other end is that you start noticing a little bit of drift. I was testing this a little bit earlier. And here it's showing 4.7, so we're actually at 25. So yeah, it begins to drift a little bit as we get to the higher frequencies in the F. Now, as far as the G band is concerned, that's the one up on top there. If you look at the drawing, it's hardwired to the F band. There is no G band on this one. I don't know why they have it on here, but maybe it's a vestige from something before. But as you see, when I throw this, there's a little bit of a movement on there, but not anything that would suggest that we're switching over to 50 megahertz rather than 25. So when you look at these labels over here, we really only go up to 25 megacycles is how they used to say it back then. Because really the G band is just a duplicate of the F band. I'm kind of satisfied with this testing. So it looks about the same. And that's the B band. We'll go to the C band. And at this point, I've got it, you know, I'm kind of bottomed out on this all the way up, so I'm going to switch it over to the times 100 magnifier and turn this down. I turn this fine-tune one down a little bit. And I'll I'll change the times to division there. So that's C, looks pretty good. There's D. This is much higher than I was able to go with either of the other scopes by now. You get to the D band, you're at 2.5 megahertz. And I can bring in, there we go. I can bring up, this oscilloscope doesn't have a digital readout on it, but it does have something called cursors, where you can set the cursors up and it'll give you a readout on what that frequency is. Basically what I'm doing is where each one of these waves crosses the line, I position one of the cursors. And it basically looks at, it does the math and tells you, okay, we're at 2.5 megahertz right now. There's the E band. I'll give it a little bit more power. Okay, so now we look at F band. Yeah, that's F, all right, okay. And here, I think I've got a little bit more power I can give it here. Turn this intensity down a little bit. And I'll increase this a little. The signal's beginning to get a little bit distorted as we get up a little bit higher. So what I'd like to do is back this thing off and see if it gets, see where it actually starts getting bad. Let me change this. No, that's too much. Now I can't really. It looks like it's good at this point. And that's around 10 megahertz. The signal is not distorted at all. What does this say it is? And again, even with the cursors, it's just, you know, it's just an approximation, but that's about right. Yeah, the signal looks pretty good when you're here, but once you get beyond that, it starts. Let's see how bad it looks once we get all the way to the other end. And I'll spread these out a little bit more. Yeah, look at that. There is some, man, that's nasty. Where's this at? About 20. But that's that's really a wild looking signal, isn't it? There's a lot of harmonic frequencies popping out in that image, I would say. Let's continue marching in this direction. I mean, some of them, they almost reconstruct to where it's nice. This one looks like a ramp almost. And then this one, winds up looking really wild. Yeah, it's not a bad looking wave when you get down to there, but between 10 and 25 it begins to really get distorted. Maybe there's something else I could set up on this. I wonder what would happen if I did try to multiplex a signal in there, or modulate a signal in there, using that external modulator jack. Let me think about that. I have another Hickok. This one's a newer model, but it was Teaching Systems one. I bought it when the Heath kit I had proved to be just really terrible. I've plugged it into that external modulator jack, and I've taken the output from the oscillator and just kind of draped it over the top of this radio I've got. Now this radio has not been restored. So I've got the two of them plugged in right now, and I'll turn on the radio. And I've got this thing broadcasting. It looks like about 1,050 cycles. And this thing's tuned. It's a little bit off, but you can hear the noise on there. Hopefully you can hear it, because, and as I turn this knob here, so it looks like I'm able to broadcast a little bit there. Let me try finding a different station and see if I can find it. It's hard to find, actually. I'll try to move this over. It's close to the same spot, but it's not exactly. There it is. So it's a super low powered antenna, so it's not going very far. It's draped over the top of my radio. If I move that antenna 5 feet away, you won't even be able to hear it. So it looks like this thing is modulating a signal from here onto the carrier frequency, which I've set now at, well, just a little over 1,000 I'm sorry, that's, what is that? 1,000 kilocycles, yeah. So, but the thing is that when I look at the modulated signal on the oscilloscope, it really looks terrible. You know, I think I'll stop this little clip for now and show you. This is the kind of envelope I expect to see when I'm looking at a modulated signal. I'll try to summarize these next few clips because they got a bit long and confusing. In this first shot, I'm showing the envelope I would have expected to see from a modulated signal. This one was generated on my WaveTech by modulating a carrier with an audio frequency. This shot, on the other hand, shows what I am seeing when I attempt to modulate the carrier on the Hickok using the external jack. The audio frequency is being fed from the WaveTech, and the scope is triggering off of the audio signal. In this shot, I'm triggering off the carrier frequency and just allowing the audio frequency to free run. It kind of shows that the amplitude of the carrier is impacted by the audio, but the envelope just appears to be reconstructed waves. Although we were able to hear the audio frequency shift around as I worked the dial during radio testing, one kind of has to wonder how faithful that demodulated audio really turned out to be. In other words, how badly would this type of modulation mangle voice or music, for instance? It seems that the OS-10 doesn't necessarily function as a true RF modulator, but as more of an RF mixer. And if so, the signal looks very much like what one might expect, with the exception of the negative skew of the envelope. Note that this bias is only associated with band A, though, and is likely a result of the poorly formed waves we saw in that band. If you've seen any of my earlier videos, you know that I kind of like to try to create a 3D model at the beginning of a project and create a cross-reference to the schematic so that it's easier to work on. And it also gives me a chance to familiarize myself with the device that I'm working on. It's kind of like just basically run through everything and get to know what it is. I couldn't really do it this time because I didn't, there wasn't enough original work in here to be able to figure out where the components all would have been. So I'm going to go ahead and make a 3D model of the as-built, as it is after I'm done working on it, which is different than what I usually like to do. But anyway, as I was doing that, I needed to go through and do an audit on everything. And I noticed that back behind these two boards, there were still, I think there were 4 more components back in there. And it kind of didn't make any sense because there were only 3 components that I was aware of that I was missing. I mean, I knew that there were probably additional components stuff back behind there that I didn't see. It's kind of hard to get back in there and see. And I knew I had a couple missed, but I knew where they were. They were right here. But it turns out that there were a couple of more that were stuffed real close behind this point right here. It was, in this case, it was 2 resistors and 2 capacitors. And, I went ahead and pulled those out. It turns out that one of the resistors and one of the capacitors did not belong where they were. I mean, if you looked at the location where they were at, it looked a lot like it was part of the original drawing, not the revised version that this device is supposed to be based upon. And the odd part about that is it's not as if somebody was going in there and making, repairs or restoring the piece of equipment. This looked like original work, like it was originally wired like that. And so that means that it came like that out of the factory. Yeah, it's kind of weird. It looks like they pulled an old one off the shelf and put the rest of the components in and ran with it. But anyway, as I pulled that out, like I say, there were 2 in there that didn't belong. So now I'm still missing one. And it turns out that there was a missing filter capacitor that came off of the plate of the primary oscillator. So, I put one in there, this little capacitor right there. It's kind of temporary tied in there because it's not really the right size. I had 10 nanofarads and I had 0.2 nanofarad capacitors, but I didn't have a 1 nanofarad capacitor. So I just put a 0.2 in there for now, 0.22 in there for now, and just to see what would happen. I went ahead and pulled the other components out from behind the board, and I've installed them on the front of the board, and that's how they will appear on the model, which is really only useful for this one device. It's not useful for any other one of these OS-10s. So also while I was in there, I did find a wiring error that I did myself. I had this capacitor here wired to the wrong lead on there. So there were several things in there that were that might have caused problems. One of them was something that I did wrong because I replaced this capacitor last. It was the last one that I replaced, and I put it in the wrong place. So, um, we are where we are right now. I didn't really notice uh, a whole lot of improvement on anything. I mean, we look like we're okay as far as um, the high end of the spectrum. Those waveforms look pretty good, but when we look at the low end, on the A band, that's where we've had problems before, or have had them for a while now. Um, I think that's about as good as it gets. Now that looks a little bit better than what we have been seeing, but if I move it up to a higher, like times 100 RF times 100, you can see we're back at that same basic look. It really didn't improve any. Um, if you look at it, this is on the A band, and before it, you could see that it was skewing to the negative side quite a bit. It's not as bad as it was. I mean, there might be a little bit of negative skew on it, but it really doesn't look as bad as it did. Let me try. Maybe I can get this in here at the same time. This switch right now is set to one of the RF settings for attenuation. But if I throw that switch all the way to the left, and if I throw this switch here to AF, you'll notice a difference, that it actually is starting to modulate a signal on there. And we can tune that in. And measure the frequency of it. And if I set these here, I can measure it. And basically it's a very loose approximation here, but you can see it shows about 366, maybe a little bit higher than that, maybe 370, about 370 cycles, which I think we calculated something like 380 or 385, but all it takes is for that capacitor to be off a little bit in order to change it to something like that. I think I went in and figured out that if that capacitor ran at, instead of 0.1 microfarads, it was running at 0.108 microfarads, it would produce this frequency that we're looking at right now, and that's entirely possible. There's another oscillator. This one is the 400 cycles, which is 371 as we just saw. And there's another one over there for 0 to 10 that I can switch it to. These are just local oscillators. I don't have anything plugged into it externally. I don't know how you calculate this. It's not a typical LC type circuit. Although there is a capacitor involved, because you can adjust, it appears that you can adjust this RF corrector, but if you look at the top, it's labeled AF in kilocycles. So I should be able to use that to modify a little bit of the AF frequency, and I found out that I can. If I turn this all the way to 0, I get a flat line, but only at this RF frequency. If I move away from that RF frequency right there, which is 167 on that dial, closer to 160 actually, then it doesn't flatline. I fall out of whatever resonance it's creating with the A band coil for that RF oscillator. But so if we look at this and think that that's zero, that's where it's zeroed out, and then I increase this, it's kind of like peaking on an oscilloscope. It gets to a max and then it starts going to a lower frequency. See how it's starting to move back away now. So if I stop right at its peak and I measure that frequency that we're at right now, and again, this is just a crude measurement, we're at 12.5 kilocycles. So it goes from 0 to 12.5 kilocycles instead of, I think that right there it says 0 to 10 kilocycles. So it's off a little bit, but it does work. And of course the wave is kind of, the actual envelope on that wave is kind of ugly, that modulated signal. So, but I thought I would show that the functionality works. I'm not sure what to make of it exactly because it's beyond my pay grade, but I thought I would show it. Anyway, most of the signals look okay. The only thing that I never really did get around to fixing was the noisiness on band A, and it's a little bit better as long as you apply the power correctly. You go in with as low power as possible that is acceptable by the device that is under test. And the other thing I didn't get around to showing on is this dB meter. Part of it's because I still don't quite understand what it's all about. I did test the meter itself. I plugged in 2.5 volts above the capacitor and behind the capacitor on both the 0 and the 25 scale that you see there. And in all cases it it caused the needle to move on the decibel meter. So the meter itself seems to work, and other than that, it's completely separated from the rest of the device. The only thing that it's connected to is there's a termination to ground. That's it. Other than that, all of its components are completely separate. There's no power being fed to it other than what it picks up off the chassis. So that's about where we wind up with this thing. I think I'm going to close it out. This thing's getting to be a little bit long anyway. So in the end, we wound up replacing 11 capacitors, and we had two that didn't need to be equipped in the device. They didn't belong in there. Almost all of the capacitors are good except for the 3 that you see in the tub right there on the top. All of those tested out of spec. It looks like I replaced 9 resistors, and I think I had one that was equipped that didn't belong in there. All of those resistors tested bad except for the big blue one way up on top up there. And off to the left is some hardware. That lamp I replaced with the jeweled lamp that you see there. And also in front is that's a nice looking switch. I'd like to try to find something to use it on. That thing goes way back, so it's kind of nice looking. I'll kind of leave it at that. As far as cosmetics are concerned on this, this is, this stuff cleans up really, really nicely. You don't really have to do very much. Bakelite is great. It lasts forever. As long as you don't put Windex on it. If you Windex Bakelite, you'll destroy the sheen right off the bat. As far as the box is concerned, I just kind of cleaned it up with a little bit of I think I used WD-40 at first and then cleaned that off with Barber's Helper, and it kind of shined it up a little bit. Looks pretty good. Um, on that, on our gauge over here, all I have is a piece of plastic in there right now because, you know, like I said, they broke it there, and they broke the glass and that needle. I was able to get the needle line back up, but um, all in all, it looks like a pretty good restoration. Thank you for watching.